So this is the very last of the homework. I will remind you guys of the schedule. So I was supposed to be traveling next week. I am technically going to be off next week, which means I'll probably be available through email, but maybe not available instantaneously through email. After next week, on Tuesday, we're going to come back with a reading assignment. And on Thursday, we're going to come back with the final exam for the course. And the final exam will be like the midterm. I will send it to you. You will send it back to me when you're done. And assuming none of you have fallen very far from your midterm performance, you'll be debating whether or not you're going to get a B+ or some sort of A. And because you guys are all doing amazingly well. I don't know. Does anybody have any questions about schedule, about class logistics, about what's going on? You know, everyone's got it. There's
just a question about the paper that reading that is coming up. Is the paper already posted?
I probably have forgotten to do that. Yeah, as soon as this thing is over, let me make sure they're posted. I think I have forgotten, but I don't actually know. I haven't been on Canvas in a while. But I'll make sure it's posted by shortly after the time we finish with class here. And it will be 2 papers. One of them will be a summary of quantitative genetics, and it will be long and hard. And the other paper will be an application, and it will be short and fun, hopefully. So imagine one of the papers will take you, the standard kind of half hour to read if you want to really understand it. And the other paper will, it's more like being a undergrad and being assigned a chapter of a textbook. It will take you 10 or 15 hours to get through it if you read it carefully. And if you read it quickly, much of it will be non-comprehensible. You're going to have to pay attention and go slow if you're going to try to understand it. There's a lot of stuff in there. It is really much more of a textbook chapter than it is really a paper. And we'll go over them in detail when you guys come back on Tuesday, and then it'll be exam time Thursday. Any other questions? So we only effectively have 2 problems left, and both problems are very, very long and hard and intricate and married together several ideas in maybe non-intuitive ways. So I'm going to take volunteers. Would anyone like to demonstrate 12 and 13 first? And the option for a volunteer is I will do it myself. And so if you guys stay silent, you're guaranteeing you're going to get my presentation of it. And unless you'd really like to do it yourself. That comes as no surprise. So let's see if I can, oh, by the way, let's turn on security so some of you could have gone had you wanted to. And now, homework 10, answers. Can you see my PDF sort of looking thing that looks at the top of problem 12?
Yep.
So problem 12 and 13 are among the most realistic problems we're going to see in this class in terms of almost like real data. And 14 for the one, not 14, it's just weird, just silly. But there are a lot of ideas going on, and you have to sort of fully grasp everything we've done to make sense of it. But once you do, it's actually relatively straightforward and easy. So in problem 11, before we left, we said 1 in 68 children have autism. And we thought about that like it was a threshold on a normal distribution. And everyone above the threshold had the disease and everyone below the threshold didn't. And if the threshold was 1 in 68, that means about 1.47% of people are beyond the threshold, which would suggest the threshold position on a normal sort of 0-1 normal distribution should be at 2.178. And that's where, if I remember correctly, we left things on Tuesday. And in problem 12, this is actually true. These numbers are the estimate of these numbers are a little bit different today than they were when I first wrote this problem. But it is true that autism is much more common in boys than girls. In fact, it's about 4 times more common in boys than girls. And at the time I wrote the problem, our best estimate for the rate of autism in boys was about 1 in 42, and our best estimate for the rate of autism in girls was about 1 in 189. So that suggests about 2.38% of boys have autism and about 0.0053% of girls have autism. So again, if we model this as a 0-1 normal distribution and a threshold, that says the threshold for boys is at position 1.98, and the threshold for girls is at position 2.56. So the way we conceptualize autism, the way we conceptualize the difference between boys and girls is girls just have a higher threshold. It takes more liability to make a girl be called autistic than it takes a boy to be called autistic. Whatever this thing, liability to autism is, it takes more of it before girls are autistic than boys. That's how we're going to model it. That's how we're going to understand it. That's how we're going to think about it. Do we have any questions so far? The implication, though, is that once you start admitting that girls and boys have different prevalences, you almost have to start doing everything that you would likely do in boys and girls separately. You have to start sort of analyzing this if you want to try to infer parameters, if you want to try to understand what's going on in boys and girls separate from one another. Because it turns out that there will be differences between boys and girls, in sometimes even significant differences in boys and girls, and things like allele frequencies and that sort of thing, caused by nothing more than a difference in threshold. And we'll see some of that going on in this problem. We'll see much more of it going on in the next problem. This problem, since the effect sizes are so small, the differences between boys and girls are very subtle. And the next problem, because the effect sizes are so, really because the prevalence difference is so large, we'll see vast differences between boys and girls.
This is
Yep.
just kind of a quick question, maybe a little too theoretical, but if we were thinking about how like a disease definition would change and that would ultimately change some understanding of prevalence, does that kind of change how we understand the genetic and then the environmental contribution? So something like autism, which we're growing to understand that usually young girls will present a little bit differently phenotypically. And so the definition of autism for them, when it's applied just with the standard of what we know for what it looks like in a young man versus like a young woman, would be different. So then that would end up changing the prevalence. But then I don't know, does that do much to change what we understand about like allele frequency and environment?
It will, you betcha. And we will see right away, by the time we get through these problems, that if your understanding of the prevalence has changed considerably, your estimate of heritability will change considerably. That if you will make very different conclusions about how heritable the trait is if you suddenly understand the prevalence is very different. And if one of those estimates of prevalence was very wrong and the other is very right, the estimate of heritability associated with the wrong prevalence estimate is going to be wrong. And one of the things you would love to see if you start doing these kind of studies and you're trying to estimate heritability is, particularly if the prevalence differences are very different, you'd love to see your estimate of heritability not really change depending on the genders of the people involved, or sexes really of the people involved. If your estimate of heritability is independent of the sex of the people you look at, even when the prevalence is very different, that gives you a lot of confidence you've probably got everything right. When they are very different, that might be evidence that your model of disease is not quite right. Either your prevalence is wrong, or something about this disease model of it being largely, say, additive variance is wrong. Maybe it's some dominance variance, maybe it's some other variance component. Other questions? So problem 13 is very, very long, perhaps, and also almost tragically easy, except for one step. So we're going to go through this in some detail, making sure everything is as peacefully easy as it can possibly be for you. But it is application over and over and over again of many of the ideas you've seen over the course of the class. And the first thing we're going to need to have front and center in our mind is Bayes' theorem, which is the probability of A and B is equal to the probability of A given B times the probability of B. Or in this particular case, I'm going to use the letter G to think about genotype and the letter D to think about disease. And the probability of a particular genotype in a particular disease state is equal to the probability of that genotype given that disease state times the probability of that disease state. And Bayes' theorem is also kind of commutative in some sense. That is also equal to the probability of the disease state given the genotype times the probability of the genotype. So because the probability of the genotype and the disease can be written as a function of the genotype given the disease, or the probability of the disease given the genotype, I can go back and forth between these two conditional probabilities by dividing by the appropriate probabilities of disease in genotype. And we will see this over and over again. This quantity here, the probability of disease given genotype, has a name in the human genetics world, in the epidemiology world. This quantity, the probability of disease given genotype, is given the name the penetrance of the genotype. So if you ever see the word penetrance, it means the probability of phenotype given whatever it is you're talking about. So the penetrance of an allele is the probability of the phenotype given the individual has the allele. The probability of penetrance of the genotype is the probability of the phenotype given the full genotype. And in this case, the phenotype is autism. So we say the probability of autism given the genotype is the penetrance of that genotype. That's a term of art, but it is a term of art you will hear the rest of your life. You probably already heard many times already. Penetrance means the probability of the observable thing, the observable phenotype, disease or whatever it is you're looking at, given the thing you're talking about, the allele or the genotype. You will discover that many of your human genetics colleagues who are not well trained in genetics don't know the precise definition of penetrance, nor do they know the precise definition of dominance. And weirdly, you will hear them confuse those two words regularly. It's the strangest thing, but you'll hear it. And it'll just be something you get used to. But penetrance means the probability of the phenotype given the gene, the allele or the genotype. Dominance, of course, refers to the phenotype of the heterozygote. All right, Bayes' theorem. We have this thing clear in our mind. We've always known Bayes' theorem. We were taught Bayes' theorem as children practically, but we will use this thing over and over again. So in the problem, it specifies we have two alleles, A1 and A2, and that the frequency of the A1 allele is 3/4. That's P is 0.75. And we're going to assume this is an additive locus, meaning the phenotype of the heterozygote is exactly halfway in between the phenotype of the two homozygotes, and that the additive contribution to liability for the A1 allele is alpha 1, and the contribution of the A2 allele is alpha 2. And we're even given values for those. For the A1 allele, we're given a value of -160, and for the A2 allele, we're given a value of 1/20th. And to check that these numbers are sensible, we recall that P alpha 1 plus Q alpha 2 ought to be 0. So 3/4 times -1/60th, I don't know, probably is -180. 1/20 times 1/4 is probably positive 1/80. All of these numbers add to 0. That's good. The problem is sensibly specified. So we already have the thresholds in boys and girls. And this problem asks us to calculate the probability of a genotype, A1, given that you're autistic, the probability of that same genotype given you're not autistic, going through all sort of 3 possible genotypes in boys and girls separately. So this is really just the same set of calculations over and over again, done separately in boys and girls. So that's what we're going to do right here. So what you're going to see in this set of tables is I'm going to have male and then female sort of as 2 different rows. And in columns, we're going to do various things, many of which we've already been given, others of which are going to turn out to be calculations. So we start with the prevalence. We're just given it. The prevalence in boys was given to be this, and the prevalence in girls was given by the problem to be that, which implies the threshold for disease in boys is this, which we worked out in problem 12, and the threshold for disease in girls was this, which we also worked out in problem 12. We were told the frequency of the A1 allele was 0.75. The frequency of the A2 allele is 0.25. That's the same in boys and girls. Boys and girls, Hardy-Weinberg should force these numbers to be the same. The problem posits that the additive contribution is the same in boys and girls. So alpha 1 in either boys and girls is -1/60, which turns out to be something close to that value. And alpha 2 is 1/20. That turns out to be about, well, exactly 0.05. So we already know what the additive variance due to this locus is. The additive variance due to this locus is P alpha 1 squared plus Q alpha 2 squared times 2. Because they have 2 alleles, this is an autosomal locus. It's just P alpha 1 squared plus Q alpha 2 squared. That turns out to be this value here. So this locus is explaining about 1/1000th of the variance due to autism. The rest of everything else, all the other genetic, all the other environmental, all the other interaction components are explaining 0.998% of the variance in autism. So for some of the calculations we're going to do, we're going to be looking things up in a 0-1 normal table. But it turns out we don't really have a full 1 variance conditional on the genotype. We actually only have 0.998 variance. So if we use a 0-1 normal table, we'll be off by 0.02%. I don't really care if you are off by that much. It doesn't matter one way or another. But I've actually adjusted my numbers by that amount. I've adjusted the variance by that amount. So I've adjusted the standard deviation by the square root of that, which is 0.999. So if my numbers differ from yours by 1/1000th, the square root of this thing, it's because I've adjusted them to account for the fact that the residual variance after I condition on genotypes is not 1, but a hair away from 1. There's really no reason for me to have done that, except when I set the problem up, I didn't remember how little of the variance was explained by this locus. If this locus had explained 20% of the variance, you would have gotten weird stuff going on if you hadn't dealt with the fact that the residual variance wasn't quite equal to 1. Now, the next line is Hardy-Weinberg. What is the probability of the genotype in the general population? P squared, 2pq, q squared. P squared, 2pq, q squared. Nothing has gone on here other than week 2 mathematics. The probability of an A1A1 genotype is just p squared. A1A2 is 2pq, A2A2 is q squared. And nothing about the setup of this problem in any way changes the fact that we are mostly going to be in Hardy-Weinberg overall in the general population. Now, what is the expected phenotype of someone given their genotype? Well, for an A1A1 individual, it's 2 alpha 1. We proved that last week. So the expected genotype of a male or a female with 2 A1 alleles is 2 alpha 1. The expected phenotype of someone with an A1A2 genotype is alpha 1 plus alpha 2. And the expected phenotype of someone with 2 alpha 2 alleles, with 2 A2 alleles is 2 alpha 2. That's what we sort of set up and derived all of last week. So the expected phenotype on the liability scale of someone with an A1A1 genotype is a little bit negative. Someone with a A2A2 genotype is a little bit positive, and someone with an A1A2 genotype is halfway in between these two numbers because it's an additive locus. And again, if we check this quick in our heads, this thing looks like 0.066, which looks like 0.066 distance here. Yep, that's halfway in between. This is all past our sanity checks. We've probably done our math correctly up till now. This is the one step where it was anything other than elementary. So we now want to know, what is the probability of disease given the genotype? We know what the threshold is. For males, the threshold to disease is 1.981. And what we want to do is find out what fraction of the distribution of A1A1 individuals is beyond this threshold of 1.981, given that the mean of A1A1 individuals is 0.033. So these individuals have a mean, not like population mean of 0, but a little bit further back from 0. So these guys are a little further from the threshold than the population average. And in fact, they're this much further from the threshold. So the proportion of the distribution of A1A1 that's beyond the threshold can really be thought of as like moving the threshold this amount further out, or moving their mean that amount back. So to find the fraction of individuals that are beyond the threshold, we can do it really just by thinking of this as a 0,1 normal or a 0.999 normal, but we'll call it a 0,1 normal. We can think of it as a 0,1 normal where the threshold isn't at 0.1981, but is just a little bit above that. It's at that number plus 0.33. If you do that and look up what fraction of the distribution will be beyond the threshold that is implied by this minus that, you'll find that the threshold, the fraction of the distribution that is beyond your threshold is 2.18%. In the population as a whole, it's 2.4. So here we got 2.18. That's all very sensible because the mean is back behind 0 a little bit. The fraction that's beyond the threshold is a little smaller than the population mean. It's just under 2.4%. It's at 2.2%, say. Similarly, if the mean is 0.33 above, if the mean of the genotype A1, A2 is 0.33 above the population mean, the threshold looks like it's 0.33 closer, and the fraction of the distribution beyond the threshold is 2.55. If you move 0.1 standard deviations away from 0, the fraction that's beyond the threshold is 3%. That same calculations we do in females, but with the female threshold of 2.56. Now we're asking what fraction of the distribution is beyond 2.56, given a mean of minus 0.033, and it turns out to be 0.0048, a little bit less than 0.0052. On the other hand, when you move a little bit above 0, you get something more like 0.0058 beyond the threshold, or 0.07.
Hey, Dave, can I clarify something?
Please do.
So, for example, for the probability of disease given A1, this is basically what you're saying is basically you're looking for the probability of liability being greater than 1.981, given that the mean of the normal random variable is negative 0.033.
Yes, exactly. I'm looking for the integral from 1.981 to infinity of a normal distribution with mean minus 0.033 and variance 0.998, which I expected you to look up in a 0-1 table, really, but then adjust the threshold by that amount using your table. But you being an adult and everyone else having access to R could have simply found this by asking R, what fraction of a normal distribution is between this and infinity, given a mean of 0.033 and a variance of 0.998. And you do the exact same thing for this, only with a different mean, and this with a different mean still. And for females, it is the exact same calculations, only it's the integral from 0.256 to infinity rather than the integral from 1.98. Is this all sensible to everyone? That is the ball game. If you can do this calculation, everything else is literally elementary school mathematics with Bayes' theorem. There is nothing more intellectually to understand. Once you've calculated the probability of disease given genotype, the penetrance of the genotype for all 3 genotypes and both sexes, you have solved the problem. Nothing more to see here, other than an accurate application of Bayes' theorem over and over again. The penetrance combined with the prevalence and Hardy-Weinberg specifies everything we need to know about this system. So with these penetrances in hand, we can immediately write down, say, the probability of disease and genotype as just the penetrance times the probability of the corresponding genotype. So the probability of being diseased and A1A1 is the penetrance of A1A1 times the probability of an A1A1 genotype, which is Hardy-Weinberg. The probability of being diseased and A1A2 is the penetrance of that genotype times Hardy-Weinberg for that genotype. The probability of being diseased and A2A2 is the penetrance of the genotype times Hardy-Weinberg for the genotype. This now is the probability of both disease and genotype. To find the probability of genotype given disease, which is what the problem asked for, all I have to do is take the probability of the two together and divide by the probability of disease. So I take this probability of disease and genotype and divide by the probability of disease, which is given here as the prevalence, and I get these values in males, and I get these values in females. So that's how a quantitative geneticist thinks disease works. They think the locus makes a contribution on the additive scale, and as a result, the different genotypes have different penetrances, and the way we observe it as geneticists is as differing genotype frequencies given disease. So you will notice that in the population at large, the frequency of the A1A1 genotype is 0.56. But in diseased individuals, the A1A1 genotype is 0.16 in boys, and it's even lower in girls, 0.508. The frequency of the A2A2, the heterozygote, is 40% in boys and 41% in girls. The frequency of the A2A2 homozygote is almost 8% in boys, and it's over 8% in girls, despite being about 6% in the general population. These are effect sizes that you could easily detect in a large genetic study of a few thousand people. So these are sort of realistic effect sizes that might be detectable in a large study. And they result in a genotype frequency or an allele frequency difference of a few percent between the general population and cases. Do we have questions about this so far?
Can you go over again your intuition for the square root of VR and incorporating that?
Yeah.
Because I kind of followed your framework here, but I didn't calculate variances at all.
Yeah, so there's no reason to, like, because of the small effect size. But so the problem posits that the total phenotypic variance is 1. So I wish I had a blackboard, but so we can break that variance down. So you may remember that one way to write the variance is the variance is equal to, the variance of X, say, is equal to the expectation of the variance of X given Y plus the variance of X given the expectation of Y. I've said it wrong. Let me, blackboard, do we have a blackboard somewhere? I don't know how to do this.
If you're comfortable drawing with your mouse.
Yeah, let me try it. So let's see. We're annotate. Let's say can I text it? So that formula look familiar to you, Taylor? Can you see a formula
Yes.
in light blue? So the total population variance is decomposable into 2 parts. The average variance given something plus the variance in the mean given that. So here we have total population variance is 1. The variance due to this locus is the variance in the means given the genotype. So this variance here is by definition that thing. That's the variance due to the locus. If I'm conditioning on a particular genotype, A1A1, A1A2, A2A2, that population of individuals, the conditioned population of A1A1 individuals, does not have variance Vx, but has variance this, has variance the expectation of the, has the, and this is the variance due to the locus. So this variance here is just VP minus that. So this genotype class and that genotype class and that genotype class does not have variance 1, but has variance 1 minus the variance due to the locus. Is that making sense to you?
Yes, thank you.
And so you could very well adjust for it, or you could very well forget it, because literally I have rounded off worse than that in all of these numbers. So it won't make any difference to you whether you do it that way or not. But if this had been a huge effect locus, you probably would have to deal with the fact, in order to get your numbers to add to 1, you'd have to deal with the fact that the residual variance wasn't equal to 1, it was equal to 1 minus the variance due to the locus itself. So, but for your purposes, for this weak effect locus, we can absolutely ignore this. Absolutely ignore that.
No, that makes perfect sense. Thank you for explaining.
Yeah. You're welcome. So the probability of the, so we've gotten the probability of the genotype given the disease, and they're equal to almost population probabilities, but a little bit less for A1A1, because his penetrance is less than the others, and a little more than the population for the other 2 genotypes, whose penetrance was a little more than population prevalence. And similarly, we can calculate the probability of not disease given genotype and the probability of genotypes given not disease. So, as the problem asked, again, we start with just the phenotype of the different genotypes. It's exactly this, nothing's changed. But here we're asking for, what is the probability of not disease given genotype? Well, if the probability of disease given genotype is this, the probability of not disease given genotype has to be 1 minus that, because those are the only possibilities. So you could find this value by simply taking 1 minus the thing above it, or you could say take the integral of the normal distribution from minus infinity up to the threshold for a normal distribution with mean that and variance equal to 1 or just slightly less than 1. You could have found that by integrating or just by taking 1 minus what you found here. So the probability of not disease given genotype is just 1 minus all of the things you've already calculated. So the probability of not disease and genotype is the probability of not disease given genotype times the probability of genotype, which is again just the Hardy-Weinberg proportions, and we get these values. So the frequency of genotype given not disease is just equal to this thing divided by the frequency of not disease, which is 1 minus the prevalence. And there you go. And what you find is the frequency of the genotypes in the not disease population, what human geneticists are prone to calling controls. The frequency of genotypes in controls is almost population prevalent, is almost population frequencies, but very slightly different, like different in 2nd and 3rd significant digits for a prevalence of 10 to the minus 2nd kind of stuff. So these are very slightly different, but very close, and their differences are almost beyond my round off error. And this is how a human geneticist tests for disease. They look at the frequency of an allele in cases, They look for the frequency of the allele in controls, ask whether those two numbers are different given the sample size. Human geneticists also wrap themselves around polls regularly for whether you're truly looking at controls or whether you're looking at population averages. And you can see the differences in frequency between controls and population overall tends to be so small you can hardly measure it for most diseases human geneticists are interested in. So you'll often find them wrapping themselves up in knots over, particularly epidemiologists do this all the time, over whether the control set was really a good control. But if it's just a random sample, you're going to get the same sort of power for your test. Just about, unless the locus is of extremely high penetrance. Does this make sense to everybody? This is how, when I look at case control data, I think about it. I take my observed genotype frequencies, back convert them into penetrances for genotypes, back converted into effects on the liability scale, and proportion of the variance explained. Another word for this thing is the proportion of the variance explained by the locus. In this case, it's 1 in 1,000. It's a very large effect locus for most human studies, human genetic studies. Explains 1 in 1,000, the variance, 1,000ths. Questions about this? I think because I went into edit mode, I can stop. So that's all I have for this problem. Does anyone want to talk any more about it? Does anyone want to show what they did? Does anyone want to sort of go through their calculations and we can compare and contrast them? Or is everybody comfortable at this point?
I do have one question about, say you wanted to approach the question by starting with the probability of no disease given genotype, as opposed to disease given genotype.
Mm-hmm.
Could you use the, like, how would you flip the threshold so that you could?
Yeah. So if I'm Taylor, what I'm doing is I'm integrating a normal distribution from -infinity up to the threshold of this with a mean of that and variance of 1, say. If I'm using a table and the table, say, gives me that, the only way around it is just go 1 minus that.
Okay, so there isn't, like, if we already know the threshold from, what is it, we had the rates.
Yeah, there's no way around this other than knowing the threshold. You can't find the probability of not disease given genotype or the probability of disease given genotype without knowing the threshold. But once you know the threshold, you can find it from a normal table, making the appropriate adjustments to the mean being not 0. Or if you are any good in R, you can probably just get it to tell you. You can actually do it in Excel too, for that matter. You can get it to tell you what fraction of the distribution is beyond the threshold or on the front side of the threshold for a normal distribution of mean something and variance something. It is, I believe in Excel, the function is called norm dist. And it may be called something very similar to that in R.
Okay, so it's not just as simple as, say, taking, so you have like, we have the rate for, let's see, for males is 1 in 42, 1 out of 42. But it's not as simple as basically finding the threshold for 41 out of 42 to find not disease. Is that right? On the table?
I would think about it, the way I would always think about it is once you found the threshold for above, below is the same threshold, it's just on the other side.
Right, that's why I'm wondering if like,
Yes, that's how to do it.
okay,
Either calculate this side or calculate that side. Doesn't matter, but you need to know where that threshold is.
okay,
And you need to know where the population mean is. But they are all either this side or that side. Other questions? Okay, would anyone like to do problem 14? Or should I just continue with it? So, problem 14 picked, so what does it say? It says we've got a big population and we've got some disease, which is at frequency 5% in males and 0.1% in females. So it's vastly more common in males. It's 50 times more common in males than females. And it says if dad has the disease, his sons have it a quarter of the time, but his daughters have it 2% of the time. And if mom has the disease, her sons have it 50% of the time, and her daughters have it 8% of the time. Okay, fair enough. I picked those numbers, 25 and 50%, because they look remarkably like Hardy-Weinberg proportions. They have nothing to do with Hardy-Weinberg. They were picked by an evil God to make you think about simple genetic mechanisms. There is no simple genetic mechanism that can possibly explain these frequencies. The only mechanism that will ever explain these relative risks is the trait is quantitative with many, many loci and thresholds. So in order to see that, we're going to build a model in males and females, in males with sons, males with daughters, females with sons, females with daughters, separately, and see what kind of inferences we're going to get. So the first thing we're going to do is say if the population prevalence in males is 5%, that implies that males have a threshold of 1.645. We're going to think about this just like the previous problem. This is autism, as far as I'm concerned. That the prevalence in males is 5%, so the threshold is 1.64. The prevalence in females is 1 in 1,000, so the threshold is a little over 3. Okay, so we now have two different thresholds, one in males, which is, 1.6 standard deviations from the mean, and a threshold in females that's way above the mean of 3 standard deviations. So that's really sort of quite a bit above. And now we can ask, much like we did with all those cattle breeding experiments, if males have a threshold of 1.64, what is the average value of a male who is beyond the threshold? What is the average value of a male who is diseased? It's the integral of x times the normal distribution from 1.65 to infinity, which you found by using those funny little pictures and tables with an I and a square root of VP in them. But that average value of a male beyond the threshold turns out to be 2.06. The average value of a female beyond the threshold is 3.37. All right. Next, let's consider sons of males with disease. 25% of the sons of males with disease also have disease. So what must the mean in males of sons be if 25% of them are beyond the threshold? So 25% of the children of males with disease, of sons of males with disease, are beyond the threshold. So if the son's mean were 0 and 25% were beyond the threshold, we would have concluded the threshold was 0.674. But here we know the threshold is actually 1.645. So therefore, we know the son's mean is closer to the threshold than 1.64. In fact, it's 0.97 standard deviations away from 0. If the true threshold is 1.64 and 25% of sons are beyond that threshold, their mean must have been 0.97 standard deviations from the population mean. Similarly, if 2% of girls are beyond the threshold, the daughter's distance to the threshold appears to be 2.05 standard deviations. We know the real threshold is 3 standard deviations away, so the daughter's mean has to be about 1 standard deviation away from 0. Now we're doing full-on cattle breeding. The response to selection of the son, here the selective force is having disease rather than breeding cattle. The response to selection of the son is RH squared S of the father. The father's difference from the mean is 2.063. Heritability is something. R between father and son is 1/2. The response by the son is 0.97. Therefore, at this locus, we infer by looking at father and son, this locus looks like it has heritability of 0.94%, of 94%. Doing those same calculations in daughters, we find the selective differential for the father was still 0.2063. The R between father and daughter is still the same. The response to daughter was about 1. Heritability turns out to be 1. So looking from fathers to both their sons and daughters, we estimate a heritability of this trait of about 100%. Let's do the same thing for mothers. So mothers, as we know, have a threshold of 3.09 and an average, the mother's average liability, those that are above the 3.09 threshold, is 3.37. Sons of mothers with the disorder have a 50% chance of having the disorder. Daughters have an 8%. Thus, the sons appear to be sitting on the threshold. If you were sitting on the threshold, half of you would be over it, half of you would be on the other side of it. So the sons appear to be sitting on the male threshold. The male threshold is at 1.645 units from 0. So sons are 1.654 standard deviations above the mean. Daughters appear to be 1.41 standard deviations from the threshold. So they are 1.685 units closer to the female threshold than unselected females. We get the response to selection of sons from mothers is equal to RH squared S. The mother's average phenotype is 3.37. The sons is 1.645. The relatedness of sons and mothers is 1/2. I estimate heritability to be 1. From daughters to mothers, the response in daughters is 1.685 units. The relatedness between mothers and daughters is 1/2. Mothers are 0.337 units above the mean. I estimate heritability to be 1. Thus, all 4 times that I've looked at mother to son, mother to daughter, father to son, father to daughter, and estimated heritability effectively independently in all of those cases, I've concluded this looks like a quantitative trait with heritability 1. And that's what it is. Well, that's how I created it. So an evil God created this trait that just happened to have frequency 25% in one relative versus another, one of their kids. It happened to be 50% in another relative versus their kid. And it is not Mendelian in any way, shape, or there's no single locus, 2 locus, 3 locus thing that's going to give you remotely these numbers. The only way to explain this trait is as a quantitative trait with many, many loci and affecting it in almost no environment, in almost no dominance, almost no interaction, no imprinting, no X-linked, no nothing. It's autosomal, lots and lots of genes. Despite some of these numbers looking intriguing, the existence of 1 or 2 intriguing numbers like a half or a quarter doesn't imply a simple genetic basis necessarily. Might, but there could always be an evil God somewhere doing this to you. But this does have a pattern you should look for the rest of your life. And it's really exaggerated here. Here, the prevalence is much, much higher in one sex than the other. Here, the prevalence is 5% in males and 0.1% in females. And the relative risk, the fraction of of relatives of males who have the disorder is something like 25% of their sons and 2% of their daughters. But the fraction of female relatives with the disease is 50% and 8%. This is the hallmark of a quantitative trait. If there's a significant difference in prevalence between the two sexes, the sex who is more rare, who has it more rarely, will have relatives more commonly affected. The sex who has the disorder more rarely, their relatives will be more commonly. The sex that has the disease more commonly, their relatives will have will have the disease more rarely. Being from the rare disease, being the rarest, the sex to have it rarely means your relatives have it more. Being from the sex that has it more often, your relatives have it less. And that is a consequence of nothing more than when you were in the rarer sex, your difference from the mean was much further. Mothers are 3.3 standard deviations above the mean on average, where fathers are only 2 standard deviations. As a result, mothers contribute a far larger average, they get a far larger average effect, a far larger response in their relatives than dads do, because they're much further from the mean. And the converse of that we saw up here, but much more weakly, that when you are the sex that has the disease less commonly, the expected frequency of alleles associated with disease are higher in you than in the more common sexed. So here A2 is more associated with disease than A1. So the frequency of A2 is higher in females than in males, but only very slightly because this has a very small effect locus. This is the pattern you look for a complex trait. If you found an allele that was actually associated and there's a significant prevalence difference between the two sexes, you expect the allele to be more common in the sex who is less prevalent. Conversely, if you look at relatives of people who have disease, you expect relatives of the less prevalent sex to be more commonly affected. When you see that pattern, you conclude it is a complex disorder with lots of genes affecting it. If you had been looking for a single or a few loci of large effect, you give up that search right there. Questions? And in problem 15, none of the numbers changed. They just gave it to you not for parent and offspring, but for siblings, but literally none of the numbers changed. And if we had gone through a heritability calculation again, we would have concluded VD was exactly 0 because none of the numbers changed. Can't really when VA is already equal to VP, when it's already fully 100% heritability. Does anybody have any questions about this?
I have a question.
Yeah.
So you sort of said like you shouldn't expect it to be that it's X-linked, but the fact that there is any sex difference at all, wouldn't that tell you that there's at least some of those loci on the X chromosome, or I guess the Y chromosome, but probably the X chromosome?
I don't know. So as a theoretician, I say the difference is caused by a difference in threshold. Full stop. And there are at least a few possible explanations for why there could be a difference in threshold. One of them is the effect of the individual loci are different in males and females, meaning that effectively the variance due to each individual locus is different in males and females. So that the reason the female threshold appears further out is because the females have more variance, because the individual variants on the liability scale are contributing more on average in females than males. That if it were all autosomal and the individual loci were making a larger effect in boys than in girls, or girls than in boys, you would have this effect. Or maybe it's X-linked, or maybe it's something else. So this is also perfectly consistent with something like what Brooke was getting at, and it's just observer bias in a weird way. That males and females are exactly the same in every way, but for whatever reason, the human being who is assigning phenotypes doesn't assign a phenotype to females until their liability is way at the tail of the distribution, but assigns it much more readily in males. And why they do that, who knows? But it is nothing more than say an observer bias in what they would consider the disease to be based on the gender they're evaluating. That will allow everything to go down the road and you'll have 100% heritability. It'll all be perfect and everything will match. And it is nothing more than we're observing it differently. But if you want to know about the effect of the X chromosome on autism, I would recommend coming to the Gen Epi Journal Club tomorrow at 10 a.m. Where I'm going to talk about evidence for X chromosomal involvement in autism. But as a theoretician at this point, I'm still saying the threshold is different. That doesn't mean anything, really. You, as, say, a biologist for this particular second, is thinking, so what? Why is the threshold different? And I'm saying, I'm not telling you. But you will get something resembling a much more fulfilling answer tomorrow if I put the talk together right.
Cool. Can you like post the link in the chat maybe? I think I don't have access to that journal club that I know of, so.
I will.
Cool. Thank you.
Let's see. No, I'll email it to everybody after class. I don't know where the link is. Is that? I'll email it after class. Maybe I can look at my own email right now, can't I? I'm smart like that.
I do also have a question about recognizing that pattern for complex traits
Yeah.
whenever.
Yep. Go ahead. I'm paying attention. I promise.
Oh, okay. So I think as I'm kind of thinking about it, it makes sense that we might see it we would see the pattern when we have two different sexes, because those are two different genetic contributors. But is that if you were to split a population in two and you see maybe you're not splitting by sex, but you're splitting by some other factor, and you see this disparity between whatever two factors you divided, does that still hold, or is it more related to like who contributing?
Nothing about this was actually due to sex. It was all due to threshold.
Okay. So basically it's a general concept and not necessarily like who is like one side of a parent half, or who's contributing what amount of, okay.
Yep. You could do this exact same analysis for whether the parent came from one population or came from whatever you want to call that, came from one group versus the other group. It just turns out that grouping people by their sex is one of the easiest things we could do. And it is something that for human disease, human doctors do all the time. They classify someone by their sex. And we have evidence of prevalence difference by sex of many disorders. So that is a natural divisor, but nothing about this was about sex, really. It was about two different subgroups that had different prevalences. This just happens to be the subgroup we look at most often. But yes, you could have, say, done this exact same analysis. Like if you were now thinking of say, proper populations, you could do this as a function of you're interested in wild butterflies. This could be a population of one butterfly versus another butterfly, populations that are highly related to one another in a breed, have the same allele frequencies, but for whatever reason, different prevalences of whatever spot you're looking at, say. And for those who are interested in like polygenic risk scores, which was like a question from yesterday or the time before, if you're now like your polygenic risk score, which has to do with the probability of the variant, or has to do with the penetrance of the variant and the allele frequency, we now see that population prevalence is wrapped up in the penetrance and in the allele frequency. That if by magic you took an allele from a population with one prevalence and moved it to a population with a different prevalence, that allele, even if it's having the same effect on the liability scale, will be at a different frequency in the new population and will have an apparently different penetrance because the prevalence is different in the different populations. So if you are interested in questions about generalizability of polygenic risk scores, when you estimate effects in one population, those same alleles in a different population with a different prevalence will have both different frequencies and different penetrances if they have the same effect on the liability scale. That's the reason mostly people struggle with applying polygenic risk scores estimated in one population to a different one. Because if the prevalence differed when going from one population to another, the allele has an apparently different penetrance and in a different frequency. Even if its effect is the same on the liability scale. So our default model in our minds is maybe as a biologist, we believe effects on a liability scale are fixed. And maybe we think they're really fixed in males and females. We think they're fixed in all populations. But when moving to different populations, because of different prevalence differences, the frequencies will appear different and even their penetrance may appear different. So that estimating how bad off someone is from their genetics when you estimated their effects in one population and do not correctly account for prevalence differences becomes really nasty. Other questions and comments? Well, that's the end of the class, really. And we'll see some papers and talk about some stuff in the papers. But that is all I have to teach on these topics right now. Next week, you will be off. You can meet together if you choose to, and as a study group, but I won't be coming. I will respond to your emails probably eventually, but not quite as fast as you might hope. But I will respond, and I will post the papers to be read in 30 seconds. And it's exam time 2 weeks from today. Questions?
Isn't it 3 weeks or?
2 weeks from today. We're off next week, and the week after that is exam, Thursday. Monday paper or Tuesday?
Oh, okay. Wait, I thought we were going to talk about the paper. Okay.
Yeah, Tuesday we talk about
Okay,
papers.
never mind.
Thursday we talk about exams. We have 2 classes a week, as it turns out.
Okay.
And these sort of details are, just the details. Let's call it 3 weeks, whatever. Doesn't matter. Questions? Okay. A week from Tuesday, paper. A week from Thursday, exam. Good luck, guys. And tell your friends who passed their qualifying exam, we missed them, but congratulations. And we hope they get over their hangovers soon.